I made a solution last night before sleeping. I cannot guarantee there's no mistake in it. So or you can just check the method. Calculation doesn't really matter. So it's okay. The first one is the Finite homework 2, or the example problem we did in class. Actually, it's simpler because we have less nodes and less elements. So element 1, 5, 2, from 2 to 3. Element 3 is 1, 1, 3. And element 4, 3, 4. So this is how we had the assembled matrix. And apply boundary condition, of course. These two are deleted, so we have 2 by 2. Stay quiet. We solve for the U2, U3. For the element force in element 2, and of course, Uj minus Ui. In this 1D, we don't really need to define what is I, what j, because normally we assume this is x-axis, and always on this side is node I, this side is node j, right? So there's no confusion. I mean, if in 2D space, we don't really know which is first. I mean, you can define a new, but 1D situation, we normally assume left, right is positive x. So Uj minus Ui. So this is element force for element 1. Reaction force, of course, you have 2 methods. One is considering back to the, because this 4x4 is simple enough, so it's perfectly fine. It's standard procedure. You have this one times this one equal to F1 and become the reaction force. So this is a simpler way. And or if you want to use, again, some students ask, like, if the method I talk in class for 2D situation, if it's applied the same to the 1D situation, of course. Because it's based on understanding, it all, of course, apply to any like similar situation, but it just does not simplify calculation. So let's say for R1 is equal to the nodal force for element 1 and node 1, and element force of element 3 and node 1. And for node element 1 and element 3, both elements are the first node for where the reaction force applied. So it is negative, negative because first node. Second node then is positive. So in this situation, then we have element force of element 1, Uj minus Ui, element force element 3, K3 Uj minus Ui, and then we get the same thing. So this is the first question in our exam. There should be no surprise, right? It's very standard spring system problem. And of course, second problem you should expect is bar system. So for this one, again, it's very similar to our example problem in class and also our homework practice. So for the K1, K2, EA of L, EA of L, and we have 3 nodes. So A, negative 8. And for second element, we have 2.5, negative 2.5, negative 2.5. So this is how we did assembly. And then for the reaction force, it's on this side at node 3. So everything related to node 3, they're gone. And in the end, we have 2 by 2. We solve for the U1, U2, and for the element force, displacement node 1 and node 2, stress at 1.5. And I emphasize in the exam review class that 0.15, it doesn't really matter. It just represents that we need to calculate stress in this element. So of course, you have the element force, you can calculate stress. And of course, as I said, stress, you can also calculate from other end. So let's say if we know the displacement at 2 and at this node and this node, so you know the wait a second. If you know the origin, you can calculate strain. And once you have strain, you times Young's motion equal to stress. So stress can be calculated from the internal force, can be calculated from the displacement. Oh, yeah. Thank you. Thank you. As I said, I made a solution last night before I sleep, so there's no guarantee I don't have mistake here. 1 point off. 1 point off. Any other mistakes? Any question? Again, this is a very standard problem we practiced. The third problem, this is my definition of node Y and node J. So you can do it any way you want. And if I define this is the local X, then this is also the global x, so it's 0. If I define this is the local x for element 2, and this is global x, global x to local x counterclockwise, 45 degree, and I have corresponding L and M. And of course, that anything related to node 2, node 3 doesn't matter because the boundary condition will be deleted anyway. But of course, if you prefer, you can write 4x4, 4x4, and 6x6, and then delete boundary condition. It's just so some of the red pages for this problem. So let's say since I define 2 to 1, so 2 2 1 1, 3 to 1 3 3 1 1. And we only need these 4 components, everything related to node 1. And do assembly. So this is from this one, and the rest part is from element 2. Any question? If you have any question, talk to me. So, and of course, I emphasize in the exam review class that K, Q, K, F. Most of the time, we have the K, we have the F, we solve the Q. But for the same equation, we can solve in different direction. We can also have we know the K, we know the Q, we solve F, right? Same equation solve in different direction. And this is a standard one. We have the K, we have the Q, it's given. You solve for F, and we're done. And for the second step, actually does not depend on the first step because, I mean, the displacement they are given, and this is really depend on displacement. So for the element force, since node 1 is the second node, so it should be J minus L U I M U I, but everything I know I is 0, so we only have one term, and EA of L. And also the M here is also 0. So in the end, this is like really simplified in terms of calculation. This is the element force, stress. And of course, as I said, stress really you can calculate from the elongation divided by original length times Young's modulus. You get the same thing. Reaction force, stress is in both elements. Stress in, okay, I calculate both. And this one is tension, and this one is in compression. Makes sense. The reaction force at node 3. So since node 3 here is the first node of element 2, based on my definition of node orders, so it's equal to negative of second element force, and it's positive. Yeah, and also it makes sense if you have force apply, if it's moving this way, and then the supporting force should be in this direction, so it's positive value. And of course, if you want to use the standard procedure, you can also have the 6x6 matrix, and the 6 components, and you calculate F1x, F2x, F1y, F2x, F2y, F3x, F3y. You can have the x and y component of the force applied node 3, and then you square root of the F3x square plus F3y square, you get R3. It's the same thing, it just take more time. You get the same answer. I just feel like this is easier, so I didn't use the second solution. But in your exam, I mean, any method is fine. You get the same point. You get the corresponding points. The last question is, of course, temperature change. Dropped by 100 degree. And the same thing, I define this is my node order. You can define in any way you want. If I define from 1 to 2, and this is the global x, so this becomes global x to local x is 30 degree. And if I define from 3 to 2, this is global x. Global x to local x counterclockwise, 45. And this corresponding L and M. Since there's a temperature change, I need to have this extra term here. So I wrote a complete matrix equation instead of just a matrix. So again, everything related to node 1 and node 3 doesn't matter. So I didn't write those components. So we only, for element 1, we only need this 4. And this term, fourth term, obviously is not 0. And we have temperature term is A alpha delta T, negative L, negative M, L, and M. For element 2, there's no temperature change. So again, 3, 2, so it should be 3, 3, 2, 2. And we only need everything related to node 2. So this term is a nodal force. We know that if we add this one and this one, it becomes the external applied force applied at node 1, node 2, and node 3. So for after assembly, we know that we need to add these two terms, and with these two corresponding terms, and we get the external applied force at node 2, which is in the x direction 10 to 4th, and in the y direction 0. So this is the external force applied vector. This is the corresponding temperature vector. And for this one and this one, don't forget the coefficient. We have, the rest part is just calculation. For the element force, this equation is provided. So based on the solved U2, V2, you can solve for, and also temperature change, you can solve the element force and reaction force at node 1. Of course, you can use the big matrix equation to solve for like F1x, F1y, and then square root something. That's a standard procedure. You can also, based on the understanding of nodal force, reaction force, and element force, the relation between them. So because our node 1 is the first node, so first node, as I said, is the negative of element force, and element force we already calculated. So yeah. It doesn't matter. You should not receive any penalty for that. Yeah. So the main part we want to check, you guys, is the understanding part. If it's a calculation error or you missing one negative sign, but your calculation, the rest like what I did, that's like 1 point off, or you have really just like you plug in all the correct numbers, but somehow there's some error in the final calculation, 1 point off. So we don't really like penalize your calculation capability. It's not the point of FEA. We just want to check if you truly understand FEA. Yeah. And also we don't really propagate error. So let's say if you make a mistake here, right? Somehow your calculation is wrong, and you get a penalty for this calculation error. And you use a wrong number here for your follow steps. As long as this part are fine, we don't give like more extra penalty for that. So we don't propagate error. So we just want to know that it's really checking your understanding. If you truly understand the FEA method. Any question? Okay, so the exam should be fine, right? It's not that difficult, I guess. Yeah. What? I will push my TA. I will talk to them today, this afternoon. I will have a meeting with them this afternoon to talk about like details of the grading rubrics, and also the grading rubrics should be based on the performance of the like all of the performance, because if it's a common mistake, I would consider it's my fault. But if it's like 100 students, only 2 or 3 made mistake, it's your fault. That's yeah. Because let's say if for 100 students, majority of students did something wrong, it basically means that I didn't explain clearly in the class. So I consider it's my fault. So I would just reduce the penalty. But if let's say 90% get it correct and 10% get it wrong, maybe I'm fine. That's what I mean. Let's continue our Where is the equation sheet? Where is the sorry, the attendance? He signed it. Okay. So the attendance bonus is really a way that me showing the gratitude for you guys that come to class and really digest class content within 15 minutes instead of like waiting until the night before the exam. So it's truly for you. What should I say? Take class. If you just sign the attendance and then leave, let's continue our content. Where is the okay, yeah, we were here. So the lecture before our exam one, we talk about we start the bin chapter, so we talk about interpolation. So we assume that nodal degree freedom already given and how to figure out the v and theta within in between these two nodes. So we use because different elements when described into different elements, really each element has its own length, and that is defined in the physical coordinate x coordinate. So to make our derived equation that's suitable for every element, we can convert it into the reference element, and it's always from 0 to 1. So this is a relation from the physical coordinate x to the reference coordinate s. And this is the relation between these two. It's linear relation, and this is the Jacobian of mapping. If you want to really say the mapping between different reference system, it's mapping from the physical coordinate x coordinate to the reference coordinate ds dx. This is Jacobian of our 1D mapping. And since we have 4 information, so we can set a polynomial with 4 unknowns. These are the 4 unknowns. So basically, for equation, we have 4 unknowns. We can solve for these 4 unknowns. And this is how we have the 4 equation and solve this. You combine these 4 equation, and this is our solution. And so basically, we identify all the unknown parameters in our polynomial. It means that our interpolation function is done, right? And this step is just rearranged in a way that we just make it a coefficient times v1, coefficient times the theta 1, coefficient times the v2, coefficient times theta 2. So we can write this in this way. So basically, it becomes the given information nodal degree freedom times 4 shape function, and this 4 coefficient becomes the shape function. And in all your homework, in your future exam, this shape function will be provided. You just need to understand how to use it, but you don't need to memorize anything. And this was the example problem we did in class. So again, of course, very straightforward application. We know the degree freedom, and you need to find the deflection function and the rotation function at function s. And also at x equal to 1.5, just need to find the corresponding s value in this x coordinate. So and today's content is about derive the k function. So we finished the interpolation. Now let's assume that we have the KQ equal to F, how to use the KQ equal to F for the bin element. So it's in chapter 3 and section 3.2, finite element equation for bin element. So we need to figure out how to have the K Q equal to F for our bin element. So again, let's start from the general situation. We have one element and we have the two nodes. And let's say at node 1, we have V1 and theta 1. And at node 2, we have V2 and theta 2. And at this two node, let's say the corresponding nodal force as a general term, it can be a force, and in being it can be a couple. So let's say the force at these two nodes, I use different color, is transverse force F1 and a couple or a moment C1. At node 2, we have F2 and C2, force and couple applied at node 2. And for this, of course, we have 4 dimorphism, so the K matrix should be 4 by 4, right? Let's say the K for this bin element, and this matrix equation I should write as V1, theta 1, V2, theta 2, F1, C1, F2, C2. And of course, the job of the content of the lecture today is figure out what the K and how to use the K. So for deriving the K, the Stiff matrix for the bin element, we can use a strain energy. Figure out, let's say, to generate this much of the rotation and deflection, what is the strain energy stored in this single element? And we can use that one to derive the K. So for this element, I use UE. U means strain energy density. Sorry, it's strain energy. Stress times strain half is the strain density, but we are calculating the strain energy within this element. So this should be equal to EI. Let's say this element is from x1 to x2, and half dv dx second derivative squared dx. So this is an equation you learn from the mechanics materials, the strain energy of bending. And of course, how we get from this step to this step, basically you learned in the mechanics material that the strain energy density is equal to half of stress times strain. And then you integrate in this whole bin, you get a strain energy stored in the bin. And for this derivation, this part, if you are interested, like how to from stress strain to get this equation, or if you forgot what you learned in mechanics material, you can talk to me during the office hour. But I do not plan to use our FAA class time to do this derivation. So we also talk about the our shape function. Sorry, deflection function is derived as function of s, but our definition of the strain energy is in terms of x. So we need to convert into the reference coordinate. So now we have, and also I emphasize the Jacobian of this 1D mapping. We need to use this one here. So because this dv dx, we need to write as dv ds, ds dx, right? Chain rule differentiation. So it is EI L cube in the reference of coordinates is always from 0 to 1. And now we have dv ds. V is the deflection at function of s. ds. And of course, I also skipped some derivation part. You can just simply consider this one as dv dx equal to dv ds ds dx, and dx ds dx equal to 1 over L. So basically, you have 1 over L 4, right? But since you have dx equal to x equal to L ds, so it end up with L cubed. So EI and everything else. Oh, this from x1 to x2 in the physical coordinate now it becomes reference coordinate 1 to 0 to 1. So that also explains why we start our beam chapter from interpolation, because we want to have a deflection function as function of s first. Then we can derive what is actually the K matrix for our beam element. So let's put the equation we learned in the last class. Basically, can write, since everything in FA is matrix vector, so let's write it this way: N1, N2, N3, N4, V1, theta 1, V2, theta 2. So this is the same as what I gave in the last class. N1, V1, N2, theta 1, N3, V2, N4, theta 2. Right? I just write in vector form. So now what we can do is that we know the strain energy, we can also write in the way. Well, let's say for 1D situation, you guys probably learned from like high school physics or something, that is half of k x squared. X is the elongation, but for this matrix vector, there's really no simply x squared. Like 1D situation, we have the v and we have theta, so it forms the degree freedom vector term. So what we need to do is that it's 1/2 degree freedom vector transpose k. And q. So this is more like the matrix vector form of half of kx squared, right? The degree freedom here function of the x in the 1D situation. And this is the stiffness for our beam element. This is the matrix. Unlike the spring system, you only have one scale, one number. K means spring stiffness. So this is the equivalent function of 1/2 of kx squared, if you are not familiar with one. So right now we have this one. So strain energy in our beam element, we derived the shape function, the deflection and function s. We can plug into this equation. And of course, there's some derivation here. I do not plan to write the detailed derivation here, but the general idea is that you plug this deflection function at function s back here. You take derivative, second derivative, square, and integrate. And in the end, you can separate in the way that it's 1/2 times degree freedom on two sides, and whatever left in between, this should be the K matrix of our beam element. It should be a 4x4 matrix. So basically, for each component in that 4x4 matrix, you integrate from 0 to 1 ds. As you can imagine, it takes some time to really for me to calculate and show you for the derivation. So, but you need to know that the general idea is what we learned in the last class. Plug back into the strain energy density, strain energy equation, and we can separate into this form. So on one side we have the Q, on the other side also Q. So Q transpose times Q, and whatever left in between, this should be the K. I will give the K matrix directly for our beam. If you are interested in deriving this K, like the details of the derivation, please come to my office hour. So this is the K matrix. it's a function of Young's modulus, of course, moment inertia, very important property of the beam bending, and the length of the beam L. And for this 4x4 matrix, L is the length of the beam. And basically, if you know what material you use for your beam element, if you know the cross-section dimension, if you know the length of the beam, you know the K for your beam element. Any question? So basically now we can connect everything we learned for the beam chapter. We have the K matrix. Force normally is given. You can solve the Q. Nodal degree freedom, right? V1 theta 1, V2 theta 2. And once we have the V1 theta 1, V2 theta 2, based on what we learned in the last class, no. Before the exam 1, we can calculate any V and theta inside your beam element. So it's kind of connecting. I can make a huge problem combining the contents in today's class and the class in the first section. But let's just focus on the content today. Let's make have a example for this part. We assume we have a beam system. That is clamped on the left side. And we have a transverse force, concentrated force applied at middle point. P equal to 1,000. 1,000 Newton. Okay. And there's a redundant support. So, and of course, in FEA, you definitely cannot, it should be not surprised for us, you cannot consider this the one beam element, because, I mean, if you have force applied here, this point should be a node. Otherwise, how can you put the 1,000 in the equation, right? For the 1,000, if you want to K equal to F, that F, there should be a node here. So at least we need to use 2. So this is element 1, element 2. And for the node, I can set this one at node 1, node 2, and node 3. And for the beam property, we have Young's modulus, moment inertia, length, and the same thing for element 2. To simplify, I just use EIL. Oh, okay. L is 2 meter. EI is 1,000 Newton meter squared. And you can see that this is a statically indeterminate system because there's redundant support here. You cannot really use statics to solve the reaction force or anything because this is redundant support, right? So I remember there was one class that we talk about. You have the beam, one B bar system. We have bar in the center and 2 sections on 2 sides, and then symmetric and clamp on both sides. And I said that is a static indeterminate system, and you can calculate the reaction force based on statics because it's symmetric. Let's say you have force applied this way, the reaction force should be both applied in this way. So you basically don't need to use FEA. You can just say, okay, 1,000 to this side, and it's symmetric about everything, and so 500 on the both sides. And one student talked to me after class that said, that cannot be solved using statics. You should combine with mechanical materials. Yes, it's correct. So basically, because that is a static indeterminate system, statics can only solve the static determinate system. So for that one, because it's simple enough, because let's say we are student engineer, when we see symmetric, so we know it's half-half. But if its force is not applied at middle point and it's not symmetric, you do need to use geometric compatibility in mechanics materials to solve that problem because it's static indeterminate. And the force equilibrium applied in the x direction can only provide one equation, but you have two unknowns. The extra equation comes from mechanics materials, which is the deformation of all sections should be 0 because it's clamped on both sides. So it's two equations, two unknowns. So you guys are correct. It's not solvable by purely statics. It's a combination of statics and mechanics materials. But the good thing is that in FEA, there's no discrimination of static determinate system or static indeterminate system. We solve everything in the same way. No matter you have redundant support or no redundant support, it's always KQ equal to F. We can always solve for it. So now let's back to this problem itself. We have the boundary condition, loading condition, material property, cross-section dimension, and the length. And of course, we need to solve or unknown degree of freedom. How many unknown degree of freedom here? How many unknown degree of freedom in this system? Anyone? The question is solve all unknown degree of freedom. How many unknown degree of freedom do we need to solve here? 3. Which 3? Yes, thank you. Thank you. So we need to be clear that the total degree of freedom here in the system should be 6 because we have 3 nodes. We have 3 nodes, and we have each node have 2 degree of freedom. Right. And everything at node 1 is fixed, 0, 0. Here, we always have a lot of students always confused about the roller support. They're like, what does the roller support means? Because some people feel like, oh, you have roller support, you have roller applied at the bottom pin joint, and it still can fly away. No, you cannot. So the roller support means that it cannot go up, but it can rotate. That is a roller support means. And of course, the difference of putting the roller support and the pin joint here is that, as I said at the very beginning of the chapter, we want to separate anything in the x direction from the bin element, when we deal with bin elements, because when there's actual force generated, we consider it a frame problem in FEA. And if you use a pin joint here, it says there's no roller support, it means that when you apply a force in this way, it will generate, in the real situation, it will generate actual force, actual stress, normal stress, right? But if you have roller support, it's basically, roller support means that it's free to move in this x direction. So those parts, any force, internal force in the x direction, they're gone. So this is why we have the roller support instead of pin. And this roller support really means that it's free to rotate, but it cannot move up, have the displacement in the y direction. So now, how do we solve for the U2, V2, and theta 3? Let's write the K for each element first. And of course, if you have the infinite amount of time, you can always write the incomplete 4x4 matrix. But let's say for our element 1 is node 1 and node 2, 1, 1, 2, 2, right? Again, you only need this 4. Make sense or not? Because you know that after assembly, everything related to node 1, they're gone. So let's write the K, the useful information for K1. 12, -6 times 2. So let's put the row index here. V1, theta 1, V2, theta 2. So, and of course, we don't really need this part for now. So this is for element 1. For element 2, how many components do we need in the 4x4 matrix? How many? Thank you. It's Friday. Thank you. Again, 1 point off. So the element 2 for the K matrix, for the 4x4 matrix, how many components do we need? Three. Yes. Because now we have 3. We only have this the V3 constraint, right? And for this element, V2, theta 2, and theta 3, they are free degree freedom. So basically, we need, if we put in the original equation, we just can ignore this part. So we have V2, theta 2, V3, theta 3, and we have 12, just the original equation, you plug in the EIL into the equation. So this is the K for 2 elements. Now I can delete this one. How to delete this one? Let's do assembly. We have 3 minutes. So after assembly should be 3x3 matrix. You just add the corresponding components from element 1 and element 2. So we have 24, 0, 12, 32, 8. V2, theta 2, theta 3. And what is the fourth term? I should write here. What are 3 components? 0 and 0. Thank you. So basically, the only given information, or the only force given here is this force applied in the negative y direction. Just no couple or moment applied at node 2. Just no couple or moment applied at node 3. So those 2 terms are 0. And solve for, we have 1 minute. I can show you the final answer. In your homework, if you need to solve a 3x3 matrix, in the end, you can use MATLAB. And I will make sure that exam is only 2x2. Actually, this one is not that complicated because we have two zero terms, so you can do it by hand calculation. Yes, we're done. Any question? Okay. Thank you for coming and have a great weekend. Yesterday I was in class and I remembered that in the exam